Okay, thank you. So first, I would like to thank the organizer to invite me to come for a long period here. Actually, I have not worked so much on the subject recently, except that about 5 years ago, was participating to a program on Bose-Einstein condensates. And then suddenly I heard various talks with the Hofstadter butterfly, and so at the time I have a student who wanted a subject, and so I proposed to her. So this is Jimena Royo-Letellier to look at this kind of problem. So we don't go very far in the direction of Bose-Einstein condensate. But at least it appears some questions which were related to all questions I looked with Johannes Jostrand a long time ago in the 90s, and also with the former student of Johannes Jostrand, Philippe Kerdelwe. So I will refer, at least in the last part, to a rather recent result obtained so about 1 year ago. Okay, I am sorry for Sasha and Gianluca, because this will be rather close to a talk I gave in Institut Henri Poincaré or in Roma once. Okay, so I have to use this. Just try to understand. So, yes, the work of Kerdelwe was related to to trying to do what we have done with Johannes Jostrand for the standard Harper's model for hexagonal model. And actually, at the time, there were two models, the triangular one and the hexagonal one. And about 15 years later, there was this graphene effect. And so if you look at this thesis of Kerdelwe, he is solving in some sense partly problems which will now take the name of graphene problem. So this, and concerning what was coming from the Bose-Einstein theory, we were interested to understand a small paper of a few pages by the physicist who was working with the Kagome lattice. So at the beginning we were trying to understand this paper, and what appears interesting for me at least is that at the end we have new problems in semi-classical analysis, and I hope to arrive to this point at the end. Okay, so for this part maybe I will go very fast, because Svetlana gives a detailed presentation of the problem. I learn new things about Harper, because I refer to Harper but not to Piles. So I go on, so this is the picture of the conference, and this was why, seeing the picture of the conference, I said that I have to speak about this. And okay. Now, of course, the main result in the past years was this proof that the spectrum for the standard Harper model is a counter set. So this is something we looked at with Johannes Jostrand, but we get only a very special result for a very special sequence of irrational numbers. But what I will do here is, in some sense, to use the first step of the proof of this analysis with Jostrand to analyze much more general symbols. So this will be quite far to this analysis of the counter structure, but it's much closer to what we have done following idea by physicists to what is the analysis when you are close to a rational. Okay, so I go on, and okay, here I think this okay, Svetlana has recalled the main thing, and I will take some time to coming back to this use of pseudo-differential operators, which was initially inspired by the work of the physicist Wilkinson, and this part was developed in collaboration with Justin. Okay, so in all the analysis, you have two choices: or you start directly of your almost mature operator and try to analyze what is the situation, or you start from the origin of the problem, that is, so like it's explained in Hofstadter, for example, paper, or probably the older paper. That is, you look at the problem with magnetic field, and the first step is to understand how you arrive to this Harper model. And so when you do that, you don't find exactly the Harper's model, but you get, at least in some region of the spectrum, you get some perturbed Harper's model. And so the physical question is also, can you do what you do for the Harper's model for perturbation of Harper's model? And so in this context, we, in the reduction we were doing with Justin, we arrived to some kind of nonlinear problem where we have a family of pseudo-differential operator depending on a parameter mu, and the question is more to define the set of mu such that 0 is in the spectrum of A of mu, than just to look to the spectrum of a given operator. But so for the simplicity, I will consider only the family A minus mu. So in this case, the problem is exactly the same. Okay, so quantization. So this is the basis of the Weil calculus. So you have a symbol. Here we will work all the time with symbols which are 2 pi periodic in x and psi, and you have a semiclassical parameter. So this semiclassical parameter can be can depend on the step where you are. It's not it has nothing to do with the Planck constant, but so it's an effective Planck constant. And so this is the way you quantize the operator. So this is a well-defined operator in L2 of R. The symbols are infinity function, and there is a good way to define this. So the idea to introduce in the quantization this small parameter, the idea is that you want to control all the norms, all the spectral quantity. You want to control them with respect to h. But of course, you also, if you start from a symbol which is independent on h, very rapidly the parameter h reappears when composing symbols and so on. Okay, and then the simplest example of this type is the Harper's model, which which I consider here as an operator on L2 of R, and the symbol is cosine x plus cosine psi, that you can see it as a finite difference operator here, and plus cosine x f of x. I will speak about two ways of understanding the Harper operator, which is actually two different ways are the way Svetlana was looking at. So either I will consider my operator working on small L2 of Z2 or on big L2, capital L2 of R. So there are ways for going from one representation to the other. These ways are isospectral, but not necessarily unitary. So you have to be careful when going from one point of view to the other. But if you are only interested in the spectrum, you can use the representation you prefer. Okay. Okay, so I just write one of the theorem which appears at the end of the series of three papers with Jocelyn, just to see that you see the flavor of the type of theorem we have. So here I define what I mean by perturbation of Harper. So it's something which is close to the symbol of Harper. So there is some epsilon here, but you should control this difference in a rather big zone going into the complex. So, and then if you want to have results which are similar to the results you have for Harper, there is a very important need to keep the main symmetries of the Harper model. That is, so the exchange of psi x with x minus psi. So there is in the symbol of Harper, there is a natural duality, which is rather trivial in this representation, which is something related to the Aubry duality in our representation. And so there is this periodicity. Sometimes we, oh yes, I have put two different symmetries. Okay, so this is the theorem we obtain with a lot of effort. So it's about 200 pages. But the idea is that we are considering only a very specific irrational number. That is a number for which the expansion in continuous fraction you impose that all the numbers which are here are sufficiently large. So this is a very small class of irrational. So in principle, the details are not always written, but you can assume that it appears only after a finite number of steps. So you are not obliged to take n1 very large. You can start, but starting from some rank, you need to be to have a very big. Oh, sorry. Okay. And then under this condition, you can prove the existence of epsilon naught. So nothing is explicit here, such that if you are sufficiently close to the Harper model in this sense, then you have the same property, that is the spectrum of the associated operators is a zero measure Cantor set.
So how do you view this? As a badly approximable number, or as a, I mean, it could be both, right? It could be a million and it still would be badly approximable.
Okay.
But,
So
I mean, what is
the idea is that we are doing semiclassical analysis, and you have a renormalization procedure, and we want at each step to recover a semiclassical problem. What is difficult is that we can do this uniformly, in the sense at each step we have a new effective Planck constant, but the small nf is uniform in all the procedure. So, okay. Okay, so this is not the main subject of my talk today. I will just work with a one-step but just hearing the talk by Svetlana, I don't know if close to in your generalized Harper's model, are there some models which are close in this sense to the Harper model, or for a suitable value of lambda 1, lambda 2, lambda 3, I don't know. So just to ask if at least for some operators we enter in the class or not.
Some are.
Okay. 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 So now a few words about how you react to this if you are playing with Schrödinger magnetic field. So this is because I don't know, according to Leonid's definition, if I have it in one group or in the other group. So I feel obliged to speak about continuous Schrödinger operator and discrete one. So the one standard origin for meeting this Harper equation is to start from a Schrödinger operator with magnetic field. So say, to simplify, constant magnetic field. It could be also periodic magnetic field. And you start from this problem, and you are at the beginning looking to what is going on, for example, as h bar is small, or you can also have other asymptotics interesting to consider. And then you consider some. Here I take the first case, the square lattice, but you can consider also other lattice. And then there are different ways to meet this Harper's model. And you can, for example, work with this quantity h bar fixed, but play with the intensity of the magnetic field. This is the so-called strong magnetic field approximation. And so in this case, you start from the Schrödinger operator with the magnetic Laplacian with constant magnetic field, and you consider V as a perturbation of this model. So the initial model, you have Landau levels, and then you introduce this V. And so in this case, you can show that at the first level approximation, you can understand the spectrum by the analysis of a pseudo-differential operator, where the semiclassical parameter is B minus 1, the inverse of the intensity of the magnetic field, and the principal symbol is simply V. So this explains, at least near the first Landau level, this explains how the spectrum is modified by the appearance of this B. So if this V is close to cosine x plus cosine x2, then you will enter in the domain of application of the theorem I was mentioning before. There are also other situations where so-called weak magnetic field approximation, and this time you start from the case B equals 0. You look to the Schrödinger operator with periodic potential. So we are in the program periodic operator. We take the Floquet theory. We look at the lowest eigenvalue. And then we see the effect of the weak magnetic field. So what is the result? The result is that in order to understand the spectrum near this first band, you have to quantize the Floquet eigenvalue. So this is lambda x b dx, which gives you the spectrum. So if this Floquet eigenvalue is close to cosine x plus cosine psi, and this is the case in the semiclassical context when you do the tunneling analysis of the Schrödinger operator in the semiclassical limit, you can again apply this. Okay. So in all these cases, in order to apply this kind of argument, you need to have initially on the potential V the symmetries, additional symmetries, in order to, at the end, for the effective Hamiltonian to get this the same symmetry. Okay, I think I go a little too slowly. So now let's come back to discrete operator in the point of view that I operate on small L2 of Z2. And the basic Harper equation corresponds to this operator in L2 of Z2. If you want to come back to the presentation of Svetlana, you have to do some Floquet analysis in one direction, and you will get a family, depending on theta, of operators working on small L2 of Z. But so, at the level of the spectrum, what I will look at is not, so of course, when when the flux is irrational, this is the same thing. But in the rational case, I am looking to the union over theta of the spectrum described by Svetlana. This is the spectrum of this operator on small L2 of Z2. Okay, so you can replace this this example, and actually you need to have a more general class to treat all the perturbation of the Harper model by introducing this. So this is, now you have an infinite matrix parameterized by Z2, and you have this invariance which represent the commutation of the so-called magnetic translation with the operator. Okay, so there is a very simple link between this point of view with infinite matrices and the symbol of the quantification. And this is simply, oh sorry, so this is simply this CMN, small c, large c, okay, small c is this value, but you have some invariants which permit to recover all the coefficients once you have given this one, and this appears as essentially the Fourier coefficient of T of x psi. Okay. Okay, so as I mentioned before, there are other lattices which are interesting, and there are also nice colored butterfly attached to each of this model. And here is another by Avron, Kenneth, Yeshoshua, so it's quite recent, about the triangular lattice. And there is also the graphene, which leads to another butterfly. So, so this I get it on the web from this group. Okay, and so I already mentioned that I propose to preliminary Oriol-Letellier to analyze another case, which is the case of the Kagome lattice. And so what I hope to show you is the appearance of new questions. And the first thing is, what is this Kagome lattice? So Kagome is not the name of a celebrated Japanese physicist, but simply a common word to describe a kind of basket. And okay, and the one who gives the name seems to be an average. This one, I hope, celebrated Japanese called Uzimi. Okay, so what is it? One way to see it is to say that I start from a triangular lattice, but I put in each cell 3 points, which are well distributed. And another way is to say that I start from a triangular lattice, but with a half length, and then I translate it in one direction, and I translate it in the other direction, and I look what I get. And so I hope, so this is the mathematical definition of this Kagome lattice, and here is the picture that you describe things. So so here you have the triangular lattice, and you see you have you can consider that you have 3 points per cell, but of course you have many other symmetries. And if you think to the small lattice, the small triangular lattice, you see that 1 point is missing. Also, so this is this kind of triangular. This is the so-called Kagome lattice. So
What is missing? I haven't understood.
Please.
What is missing? I haven't understood.
If you want to, if I take so I speak about this. Oh, sorry. If I speak of the large, sorry. I tried. Okay, I will try to be. What is okay? There is a big triangular lattice, and there is a small triangular lattice.
Okay.
So if I speak about the small triangular lattice, and there is 1 point missing. Mm-hmm. So you have a kind of hexagon appearing. Now, if you now look at each of these, if you look at each of these points, it has 4 neighbors with a lot of symmetries. Okay. So there are one question which in some sense comes from this the origin of the problem related to Bose-Einstein condensation. This is a question I was not thinking at all 20 years ago. But so the question is simply, can we realize concretely a potential which has the symmetry of the Kagome lattice? Just so, of course, you can say I put some theorem. I assume that I have a Schrödinger operator, that you have wells, and that the minimum are non-degenerate, and so on and so on. But for the physicist playing with ultra-cold thing, the question is, can we realize this by using our laser? So in this case, it's rather simple to prove that you can produce a Schrödinger operator with constant magnetic field and with a potential, an periodic electric potential in the sense of respecting the symmetry of this Kagome lattice. So the answer is yes. this is not exactly correct in the sense that maybe you will need too many lasers to realize concretely your potential. But at least you can produce this kind of model by using trigonometric polynomials. Okay, so here it's a picture of what you can get by this trigonometric polynomial. So the minima of the potential, the electric potential, appear on the center of the black zones. So here, 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 and in the middle you have a maximum. Okay, so in some sense we have produced a Schrödinger operator with constant magnetic field and with an electric potential for which the minima are on this Kagome lattice, and which have all the good reason to satisfy all the assumptions of a theorem.
Minima are all at the same level.
Yes, yes, we have the symmetry, yes.
And for blue and red and green, it's all at the same level.
Let's see, I come back. Yes, yes, I have 6, I should have 6 minima. 1, 2, 3, 4. So now if you think of semi-classical analysis of this problem, you have a system where you have non-degenerate minima and each well interact with at least 4 wells. So this is the part which is not completely rigorous, because this notion of to be close in semi-classical analysis is related to the Agmond's metric. And here I show you some picture where you see the picture with the standard metric. So there are points here which have not been verified, except in the limit of very large order trigonometric polygon, because in this case we can see the limit. We can see at the limit that in the middle it tends to a constant, and so there is a strong barrier inside. Okay. So now I come. So behind this there is a lot of semi-classical analysis, but I switch now to the kind of models you will find for getting the tunneling effect of the wells which are far from the initial one. So first I recall the Harper model. So this is the standard thing. Maybe I have unfortunately changed the notation. So when you are doing semi-classical analysis, you don't get exactly this, but you get this with multiplied by a tunneling term, which is exponentially small. So you forget this, because we can dilate things, and then you look the contribution of this exponentially small term. And here is what you get. Okay, and this gamma is related to the initial flux of the magnetic field through the fundamental cell, maybe divided by h bar or something. And now you can forget completely the initial problem, and you just keep gamma as this new parameter. Now, if you want to continue, or you look, you are doing semi-classical analysis near gamma equals 0, or you try to do semi-classical analysis near gamma over 2 pi equals some rational. So, and you just try to understand how the spectrum behaves for gamma over 2 pi close to some rational. And in this case, the rule is first to in the ration. If you want to look close to a rational, the first thing is to understand the rational case. And there is a standard analysis which reduce the analysis to the analysis of the eigenvalue of a family of Q times Q matrices depending on the Floquet parameter. Okay. In this context, there are two matrices which are rather explicit. Here you take the square, so at least for p equal 1, you take the square root of the identity, and you have this matrix JPQ here, and another one, KQ. So the power Q of each one is the identity, and the important thing is that these these two matrices, okay, it's not written, are not commuting. So is GK equal exponential I gamma KJ. So you
matrix JPQ is indexed by P and J.
What is wrong? P. JPQ, P, the index PQ is relative to P over Q.
So that's what Q is fixed.
Oh, yes, there is a mistake, yes. Sorry.
Q by Q matrix.
Yes, it's a Q by Q matrix, and maybe I use the same letters for two different things. Sorry. Well, I'm lost. No, I'm going in the wrong direction. No? Oh, sorry.
Lawrence will come back.
Yes, okay. No, it's okay. It's okay. So P, Q are fixed. So this is a Q by Q matrix. And where is it? And J here is between 1 and Q. And here,
I also.
and here it's okay. I have two parameters describing this time the line and the column of the matrix. Okay. Now, if you want to analyze typically the Harper's model using these matrices, so you rewrite the operator using these two matrices, and you get these Q by Q matrices. And so the bands that you observe for when the flux, the renormalized flux, is equal to P over Q, are just the bands obtained by looking at the eigenvalue of these matrices and looking to the image when you theta 1 and theta 2 go through 0 to pi cross 0 to pi. Okay. So one way to do this computation of the eigenvalue is just to look at the determinant. And the determinant for Harper's model is quite simple, in the sense that he has the structure to be a polynomial of order Q, and then the dependence with respect to the theta 1 and theta 2 is just in the constant term. And so this is one way to analyze this problem, and this is, as far as I understand the history, this is the so-called Chambers formula. Okay. So now about the other models. So the second one is the triangular model with an additional parameter here. So in some sense there are two flux appearing in the problem. So here you start like for the Harper, but there are new terms, J, K star and K G star. And the standard triangular model is with phi equal minus gamma over 2. So I have not recognized in the talk of Svetlana, this is not the same representation. When you say that you contain the triangular lattice, the representation is, I don't see the link, the direct link with this one. But so there exists also a Chambers formula in this case. It's unclear who was the first to establish it, but at least implicitly it's known. And so this has the same structure. So there exists a polynomial of degree q, and then here the constant term, so is cosine q theta 1 plus cosine q theta 2 plus cosine q theta 2 minus theta 1 with a possible shift. And this is exactly cosine x plus cosine psi plus cosine x minus psi is typically the symbol of the that you find if you look at the triangular Harper model. Okay, so this is a second case. Now the hexagonal case, which is one case where you can use apparently the name of graphene case. Now it corresponds to a system where you have a triangular lattice, but you have two minima per cell. And so the way to when you try to solve this problem, you have to have a discrete system where instead of L2 of Z2, you have L2 of Z2 with C valued in C2. Just to, and so what you get for a rational P over Q, you get a 2Q by 2Q matrix. And here I put it by block. So each block is a Q by Q block. And here it has the simple structure, which is here. So this is what you get for this. Maybe they are not a unique graphene model, but and this appears already in the PhD thesis of Cadele. Now, if you take the square of this, you recover the previous model. So this is a kind of Dirac structure. Okay. Now I was asking to Jimena Arroyo Letelier to look at this Kagome lattice, and so this was not a completely easy stuff to determine what you get exactly. But here is what you get. Now you have three wells per cell. So it's natural that you find a system which is valued in C3 for the first thing, or 3Q times 3Q. And so this is the structure. So this was close to something which was written by Hu, except that Hu was assuming that omega equals 0. But the semi-classical analysis does not lead us to think that omega is automatically 0. So we finally have two parameters, gamma, which is the flux through the cell, and a new parameter, omega. So it looks rather bad. But and the new fact also is that now you will gamma quantize later, but no, we will H quantize near P over Q, but the gamma here appears also in the picture. Okay. Now I have already mentioned that we meet this in the analysis of the triangular model. We meet this symbol cosine x plus cosine psi plus cosine x minus psi. Now, so K is for Kagome. What is the characteristic polynomial of this horrible matrix. And so, in particular, does it exist a Chambers formula? So at the beginning, you start with Q equal 2, and so you start to find the hope that maybe there is also a structure for this, and then that you will have. So here it's the result for the graphene first. The graphene. So essentially, I mentioned that if you take the square, then you come back to the triangular lattice. So this appears here. You have a lambda square here, and here it's T for triangular. So it's rather easy to deduce the determinant of the graphene case to relate it to the determinant of the triangular case. Okay, and now after many efforts, so this was obtained after in collaboration with Kerelwe, we do it after. So what is here is the structure of the determinant that you get in the case of the Kagome lattice. And so, there is a polynomial here, this time of degree 3q, so this is natural. But now you lose the fact that the other term, the dependence with respect to theta, is in the constant term. So you get, which looks quite nice, you get this cosine x plus cosine xi plus cosine x minus xi. So the Kagome, this Kagome lattice is strongly related to the triangular lattice, in the sense that you recover the object that you have found in the case of the triangular. So I'm in a terribly bad situation. So you recognize this, but so you have the structure of a polynomial of degree 3q plus these symbols. Okay, graphene, I approach. No, I go too fast. And so what do you get? You get this polynomial where you see the dependence with respect to the Floquet parameter times another polynomial of degree q. And so if you want to understand the spectrum, you have to look at the structure of the eigenvalue, the zeros of this. And so what you observe is that there are cases where you can, it's not excluded that you can find an eigenvalue which is actually independent of the parameter if this polynomial and this one have common zeros. And this is the new phenomenon that we observe for this model. For some value of omega, p and q, we can meet eigenvalue which are independent of the Floquet parameter. And so this is what we call a flat band. I'm not sure this is the correct terminology, but at least this is what I call a flat band. Okay, so that means that if you look, at least for this rational case, you have bands and possibly points, and this point could be inside the bands or outside the band. And so here are various examples. Actually, we started with examples, and then it takes some time to get the proof of the general situation. So here you have different examples. So that you get in the analysis of the common zeros, you get this or this. So with much effort, for example, in the if you come back to the Schrödinger operator of a magnetic field, with much effort we arrive to prove that omega tends to 0 in some semiclassical limit from the initial point. So it's not physically irrelevant to look at omega equals 0. Okay, so here are examples where you can compute the different things. Here you see that you have touching, the bands are touching at square root of 3 here and here. And this model, so we have other things. Here, here you have this value, -2, which I think which is isolated, and then you have bands. Okay, so you have at least in the pictures you have this kind of case can occur. Now the picture is not good, and I am missing somebody to produce the colored adapted butterfly. But I don't know if you see something. But at least if you have slept a lot of time with the butterfly, you see that there are points here which looks quite different from what you observe for the standard of or the triangular or the hexagonal butterfly. So, and this corresponds. So there are many things to understand in this picture. And so, okay. So my last part, which is a 5-minute part, is to try now to do the semi-classical analysis near. So now I am close to a rational. So this part of the analysis was done in essentially in the paper with Justron, the second one, where we do the analysis near rational. But here there is something which was not at all analyzed, is what is going on close to this. If you have an isolated point, so what you can do? Yes, in this case, what do you have in the semi-classical analysis? So you start to do the same thing as in the old papers, and what's going on? So here is typically the principal symbol. So I don't remember for which parameters. I take omega equals 0, gamma equals 4 pi, and then I look close to 4 pi. So first I quantize the matrix I have written before. And so I get, here is the symbol of this quantized thing. So, and then because if I diagonalize this, I will have a constant, I will have a constant eigenvalue, and the remainder of the spectrum, which depends on x psi. So I try to diagonalize the principal symbol, and so for the principal symbol, I don't remember if 0 was the isolated eigenvalue or if I have made a translation, but I arrive to this. So I have I can diagonalize by block, B-L-O-C-K, not block, and I have 0 here, and then I have a 2 by 2 matrix here. For which the eigenvalue, so are explicitly written here, do not meet 0. So I have separation of the spectrum. And now I want to perturb. So there are different ways to do this, but here, if you want to do this globally, and with a matrix U0 of xi, which is 2 pi periodic, you naturally meet the question of the triviality. Can you do, of course, you can do it locally, but the question is, can you do it globally on the torus? And for this specific example, you can do it by hand. Another way, which was observed by Gianluca, is to use a general theory which applies, because we know that the kernel is trivial, so we have a choice of the kernel which is trivial. And the question is, can we find a basis of the orthogonal space? And so this can be done by hand or using the fact that the sum is trivial. So in this case, you can apply this kind of general criteria. Now, okay, you have solved the principal symbol, but so principal symbol is 0. So as in the previous talk, everything is in the computation of the sub-principal symbol. So in the Weil calculus, the sub-principal symbol is just the symbol coefficient of h. So that if you can use the Weil calculus, the sub-principal symbol is the right one. It's just a symbol for coefficient of h. So so here you have a lot of computation to do. It's not so easy to compute the semiclassical symbol, sub-principal symbol, but so you can follow the general calculus. And so the good surprise at the end is that you have a nice formula for the sub-principal symbol. And the good surprise, so you get, so this is a total symbol, but the first symbol is 0 and the second one is h times what? This is a function of p delta. That is, this is the function at the level of the principal symbol. This is a function of what you get for the triangular lattice. And so, if you are optimist or lazy, so in order to stop to continue, you can think that you are just at the first step of a renormalization. But this is only the first step, which is different for the Hu model. And then what you get a function of the triangle, the Hofstadter operator on the triangular lattice, and then go on. But for the triangular lattice, to my knowledge, it has not completely achieved. So Kerdelui has worked in this direction. But, there are no complete proofs. So I don't know if somebody get that for the triangular lattice, there is a counter set structure for any rational. I don't know. This is open. So I think I will stop here. So. Yes?
So is it correct that P delta is a principal symbol for the triangular lattice, right? So P delta is a principal symbol for the triangular lattice.
Yes. It's cosine x plus cosine psi plus. So you get a function of this. But if you think of spectrum at the level of the principal symbol, so what you have not proved is that all the terms could be expressed as a. But so this is a good indication that probably after one iteration you arrive to a structure which is just the structure of a function of so this. But after one step, your renormalization is you come back to the analysis to some semiclassical analysis of the triangular lattice.
About this Cacomi-lattice. What I know is that the difference between the Cacomi-lattice and this triangular hexagonal and the sphere. If you just look at the discrete Laplacian, then the Cacomi-lattice allows locally supported eigenfunctions, which are just maybe supported on the hexagon. And does this have maybe any influence, or does the Cacomi-lattice has different phenomena than the other three?
I don't know. I don't know why the physicists look at this model. So this I have not understood.
You have examples in which the flat bands produce embedded eigenvalues in the.
Here in the yes, I think I don't remember, but. We don't analyze this case, but because it's more difficult to. So we start with the easiest case. But I think yes. Or it could be, just that at the border of another one. But the semi-classical analysis should be more complicated because we choose to just to do the case where it's the most simple, that is the flat band is outside the other band. That is simple.
So let's thank the speaker.